Chapter 1. The Limit. 12 kilometers. That number sounds almost disappointingly small. 12 kilometers is the distance a fit person runs in an hour. It is the altitude at which commercial aircraft cruise. It is, by any ordinary measure, not far at all. And yet 12 kilometers straight down into the earth is the absolute limit of everything humanity has ever achieved in its attempts to reach the interior of its own planet. Not 12 kilometers reached quickly and then abandoned. 12 kilometers reached after 24 years of continuous drilling with the most advanced equipment the Soviet Union could produce, by some of the most determined engineers in the history of science, and then stopped, not by a decision, but by the planet itself. The Kola Superdeep Borehole sits on the Kola Peninsula in northwestern Russia, near the Norwegian border. From a distance, it looks like an ordinary industrial site, a collection of buildings, a rusting metal structure, abandoned equipment. The borehole itself is a hole in the ground, 23 centimeters in diameter, smaller than a dinner plate. Through that opening, between 1970 and 1994, Soviet scientists attempted something that had never been attempted before and has not been equaled since. A direct investigation of what the Earth is actually made of, as opposed to what mathematical models suggest it should be made of. Before Kola, everything geologists knew about the deep interior of the planet came from indirect observation. Seismic waves generated by earthquakes pass through the Earth and change speed as they move through materials of different densities. By measuring those changes, scientists had constructed a theoretical model of the planet's interior, a layered structure of granite giving way to basalt, basalt giving way to mantle, mantle surrounding a liquid iron outer core and a solid iron inner core. It was a compelling model. It was widely accepted, and almost every specific prediction it made about conditions at depth turned out to be wrong when Kola gave humanity its first direct data. The project was born in competition. The United States had launched Project Mohole in the early 1960s, attempting to drill through the ocean floor to the mantle. When that project was canceled in 1966, Soviet scientists proposed an alternative approach: drill not into the thin oceanic crust, but into the ancient, stable continental shield of the Kola Peninsula, where the rock was among the oldest on Earth, and where scientists hoped the conditions might be more predictable. The Soviet Council of Ministers approved the project in 1962. Drilling began on 24th of May, 1970, and it would not stop for nearly a quarter of a century. In the first years, everything proceeded more or less as planned. The drill descended through the upper layers of granite, and the rock behaved as the models predicted. Temperatures were within acceptable ranges. The equipment held up. Engineers were confident that they were on the verge of something historic. And they were right, though not in the ways they expected. The first surprise came at around 7 kilometers depth. According to every geological model, granite at that depth should have given way to basalt, a denser, darker rock that was supposed to form the lower portion of the continental crust. The basalt never appeared. Instead, the drill kept moving through granite. Fractured granite, saturated with water and gases, behaving in ways that contradicted everything the models had predicted. The theoretical basalt layer simply did not exist. The model that geologists had built over decades of seismic data interpretation had described with great mathematical precision something that was not there. And then the temperature started rising faster than it should have. The models had predicted around 100 degrees Celsius at 12 kilometers depth. The actual temperature was 180 degrees, nearly twice as high. That difference, 30 degrees versus 180, was not a minor calibration error. It meant that the entire thermal model of the continental crust was fundamentally incorrect, and it meant that drilling deeper would require solving problems that no one had anticipated, using equipment that had not been designed for conditions that were not supposed to exist. This is where the real war began. Not the war between nations that had funded the project on both sides, but the war between human ingenuity and the physics of a planet that was in no hurry to be understood. Chapter 2. The War Below. To understand what the Kola engineers were actually fighting against, you need to understand what rock behaves like at extreme depth, and why that behavior makes drilling not just difficult, but at a certain point, physically self-defeating. On the surface, granite is what we think of when we think of hard rock. It is the material of mountains, of ancient monuments, of kitchen countertops. At surface conditions, it is rigid, brittle, and strong. Drop it and it shatters. Hit it with a chisel and chips break off. It resists deformation. At a depth of 12 kilometers, under a pressure of approximately 1,000 atmospheres, the weight of a kilometer of rock pressing down from every direction simultaneously. Granite is no longer what we would recognize as rock. The same material, under those conditions, flows. Not quickly, not dramatically, but steadily and relentlessly. Under sufficient confinement pressure, even hard crystalline rock deforms plastically, filling any void that appears within it over time. The technical term is plastic deformation, and it is the central reason why drilling very deep is not simply a matter of building a longer drill string. The process the Kola engineers described works like this. The drill bit, equipped with sharp tungsten carbide or polycrystalline diamond inserts, rotates at the bottom of a steel pipe column that can weigh several hundred tons. In normal conditions, it cuts through granite the way a hole saw cuts through wood. Progressive, controlled, predictable. But at depth, as soon as the bit removes material from the bottom of the borehole, the walls begin to close in. The plastic rock, under enormous pressure, creeps slowly toward the void left by the drill. The borehole does not stay open the way a hole in wood stays open. It tries to seal itself. This creates a problem that becomes progressively worse as depth increases. To change the drill bit, which wears out and must be replaced regularly, the entire pipe string must be lifted to the surface. At 12 kilometers, this process takes approximately 18 hours of continuous work. The string must be unscrewed section by section, each section laid aside, until the bit at the bottom is finally retrieved, replaced, and the whole process reversed. During those 18 hours that the bottom of the borehole is unoccupied, the plastic rock moves. The borehole narrows. When the new bit arrives back at the bottom, the engineers often find that they must re-drill through material that closed in during the replacement operation, effectively losing part of the previous day's progress to gravity and geology. The Soviet engineers described this as a war. Every meter gained was a negotiation with the planet, and the planet had effectively unlimited patience and an inexhaustible supply of pressure. The drill string itself added to the complexity. A column of steel pipes 12 kilometers long, hanging under its own weight of several hundred tons, is subject to forces that have no equivalent in normal engineering. The metal twists under torsional stress. It vibrates at resonant frequencies that can amplify small oscillations into violent shaking. At certain depths, engineers noticed that the string was literally rotating like a corkscrew under the combined effects of the drill's rotation, the string's own elasticity, and the resistance of the rock. Breakages were common. A pipe joint that fails at 12 kilometers depth is not a simple repair problem. The broken section, several tons of metal, sits at the bottom of a hole barely wide enough to accommodate it. Fishing operations, the industry term for retrieving broken equipment from deep wells, become exponentially more difficult as depth increases. On several occasions, the engineers were unable to retrieve the broken equipment at all, and had to abandon that section of the borehole and start a new deviation several meters away from the obstruction. Years of work lost, new paths opened. The borehole, which was never straight to begin with, accumulated a complex three-dimensional curve as each deviation added another bend to the overall trajectory. Through all of this, the data coming up from depth was accumulating and proving to be worth the cost. Because the rock that was fighting the drill so hard was also revealing, in the samples, it gave up on the way out, a picture of the planet's interior that no seismic model had ever suggested. And that would change the way scientists thought about Earth's chemistry, biology, and thermal history for decades to come. Chapter 3: What Should Not Exist. The scientific team working on the Kola project had assembled a set of predictions about what they would find at various depths. These predictions were based on the best available geological models, the accumulated seismic data of a century, and well-established physical and chemical theory. At approximately 7 kilometers depth, according to the models, the granite should have given way to basalt. The rock should have been dry. No water could penetrate through solid, monolithic, crystalline rock to those depths. Temperatures would be approximately 100 degrees at 12 kilometers, and the rock, while compressed, would retain its basic character as rigid, crystalline material. Every single one of these predictions was wrong. The absence of basalt has already been discussed. The granite continued to 12 kilometers without the expected transition, indicating a fundamental error in the interpretation of seismic data that had been used to build the standard model of crustal structure. But the water discovery was, in some ways, even more disorienting. At 7 kilometers depth, in rock that should have been perfectly dry, the drill encountered zones saturated with hot, mineral-rich fluid. Not traces of moisture, not dampness. Significant quantities of water, under enough pressure that it could flash to superheated steam upon entering the lower pressure environment of the borehole, with enough force to destroy equipment. The initial response was denial. The lab teams assumed contamination, that water from the surface or from shallower levels had somehow worked its way into the samples. They ran the analysis again. The water was still there. They ran it again. Still there. Eventually, the evidence became undeniable, and the scientists were forced to reconsider the mechanism by which water exists at depth. The explanation that emerged is now accepted as correct and has significant implications for understanding Earth's chemistry. Water at depth is not always surface water that is seeped downward. Some of it is produced in place, formed by the combination of oxygen and hydrogen that are released from the crystal structures of minerals under the extreme pressure and temperature conditions of the deep crust. The minerals, compressed beyond certain thresholds, essentially expel their chemically bound water as the crystal lattices rearrange under load. This water, generated within the rock itself, is called juvenile water, and its existence at Kola depths had been theorized but never directly confirmed before the Kola samples provided the evidence. The implications extend beyond chemistry. If water is present deep in the crust, generated by the rock, not infiltrated from above, then the entire model of what the deep crust is like as a chemical environment needs revision. Water is a solvent. It dissolves minerals, transports ions, facilitates reactions. A deep crust that contains significant quantities of water is a far more chemically active environment than a dry one, and the presence of water changes what biological and geological processes are theoretically possible, which brings us to the most extraordinary discovery of the entire Kola project. At a depth of more than 6,700 meters, in rock that is approximately 2 billion years old, biologists examining the drill core samples found what they initially did not believe: fossilized microbial life, not one species. 24 distinct species of microscopic, single-celled organisms, their carbonaceous remains preserved in the ancient rock under conditions that physical theory says should have long since destroyed them. The preservation mechanism is still not fully understood. At depth, rock is hot enough that most organic compounds should break down rapidly. The leading hypothesis is that the organisms were entombed rapidly in mineral deposits that formed around them, essentially encasing the biological material in a geochemical shell that protected it from the thermal degradation that would otherwise have destroyed it. Whether or not this explanation is complete, the fact of the preservation is beyond question. The samples have been analyzed by multiple independent teams, and the biological origin of the preserved structures is not disputed. What this discovery means for biology is profound. If life was present at more than 6 kilometers depth 2 billion years ago, then the biosphere of the early Earth extended far deeper than any model had proposed. The deep subsurface of the planet may have been, and may still be, a habitat for microbial life, protected from surface conditions that would be lethal to organisms adapted to the deep, chemically active, water-rich environment of the crust. Research since Kola has found living microbial communities at depths of several kilometers, in South African gold mines, in deep aquifers, and in oceanic crust samples. The Kola discovery was the first direct evidence that life at such depths was not just theoretically possible, but historically actual. Along with water and microbial traces, large quantities of hydrogen, helium, and methane came up with the drill returns. The concentrations were high enough that the drilling site became a permanent fire hazard. Workers monitored gas sensors continuously. Welding and cutting operations that would be routine on any normal construction site were prohibited in the vicinity of the borehole. The Earth, it turned out, was not a passive object being explored. It was an active chemical system, and it was exhaling. Chapter 4: Sounds from Hell. In 1989, a story began circulating in Western media that was, by any measure of journalistic standards, too good to verify carefully before publication. Soviet scientists drilling the Kola Superdeep Borehole had, according to the story, lowered an ultra-sensitive microphone to the bottom of the shaft. What they heard stopped the project. From 12 kilometers below the surface came the sounds of thousands of human voices screaming, moaning, howling in torment. The recording was described as proof of the literal existence of hell. Within weeks, it had been broadcast by radio stations across Europe and North America. Missionaries used it in sermons. It appeared in supermarket tabloids alongside photographs of alien autopsies and celebrity affairs. The recording was a fabrication. The audio was assembled primarily from a 1972 Norwegian horror film and had no connection to any Soviet drilling project. The story itself was traced to a Finnish Christian broadcaster that had presented it as fact in 1989 without verification. Once the myth was in circulation, no amount of debunking could fully stop it. It has been periodically rediscovered and republished in the decades since, each time with new embellishments, and it continues to be taken seriously by a significant number of people today. But the actual acoustic story of the Kola borehole is, in its own way, more genuinely unsettling than any fabricated recording of demonic screaming. The engineers and scientists working on the project did use acoustic monitoring equipment. They had to. Acoustic sensing was an essential part of the engineering instrumentation used to monitor the behavior of the drill string at depth, detect changes in rock structure ahead of the bit, and register the microseismic activity of the surrounding rock mass. The sounds that this equipment picked up were not screams, but they were not nothing. Granite, under 1,000 atmospheres of confinement, pressure is acoustically very different from granite at the surface. The extreme compression changes its elastic properties, turning it into what engineers describe as a resonator, a material that amplifies and propagates certain frequencies very efficiently. Any fracturing of rock at depth, any failure of metal under load, Any sudden release of gas pressure from a cavity produces an acoustic signature that travels through the dense, compressed rock and arrives at surface sensors transformed beyond recognition from the original event. The pump systems that circulated drilling fluid through the borehole produced rhythmic pressure pulses at several bars of amplitude. Pulses that, transmitted through 12 kilometers of metal pipe and rock, arrived at surface monitoring equipment as low-frequency oscillations that could not be immediately attributed to their source. The turbines running the drill produced broadband noise that, passing through the complex acoustic filter of the borehole, emerged at the surface as a shifting, partially coherent sound that human pattern recognition instincts interpret as voice-like. Engineers working night shifts on the acoustic monitoring equipment reported finding the sounds psychologically disturbing even when they understood exactly what was causing them. Project director David Guberman documented several incidents that illustrate why the acoustic environment of a deep borehole creates genuine interpretive difficulty. On one occasion, the drill simply dropped several meters into a void, a cavity in the rock that should not have been there by any calculation. The sudden pressure change created an acoustic event that arrived at the surface monitoring station as what the engineers described as a sharp blow, a sound with no obvious source and no immediate explanation. In the seconds after it occurred, before the engineers had worked out what had happened, it produced genuine alarm. The explanation, a gas pressurized cavity that had fractured the surrounding rock, was found quickly enough. But the experience illustrated that the deep earth generates acoustic phenomena for which even expert observers do not always have immediate explanations. What the sounds of Kola actually were, when stripped of mythology, is a portrait of a dynamic planet. Rock at depth is not static. It creaks and shifts under the redistribution of stresses caused by the borehole itself. Gas under pressure fractures its way toward lower pressure zones. Metal under extreme combined loads, compression, tension, torsion, thermal stress, fails in complex ways that produce characteristic acoustic signatures. The planet is, in an entirely literal sense, alive. In the mechanical sense of the word, constantly responding to the disturbance that drilling represents. The engineers who worked there were listening to that response 24 hours a day for more than 2 decades. The legend of the sounds of hell tells us something accurate about the experience of drilling deep, even though everything it says about the content of what was heard is false. Something genuinely strange comes out of the earth when you listen to it carefully enough. The strangeness is not supernatural. It is the strangeness of a system far more complex, dynamic, and surprising than any model had suggested. A system that, the more closely it was examined, the less it resembled what the textbooks said it should be. Chapter 5. The Ocean Route. While the Kola project was proceeding on the Kola Peninsula, a parallel line of thinking was developing in scientific communities on both sides of the Atlantic. The logic was straightforward and compelling. If the goal is to reach the boundary between the crust and the mantle, the Mohorovicic discontinuity, or MOHO, then drilling through the continental crust, which averages 40 kilometers thick, is taking the long route. The oceanic crust is 5 to 7 kilometers thick. The MOHO lies much closer to the surface under the ocean floor than under any continent. Why not drill from the ocean? The practical challenge was immediately obvious to anyone who had thought about offshore drilling for more than 5 minutes. To reach the MOHO through the ocean floor, you first had to get to the ocean floor, typically 3 to 4 kilometers below the surface, and then drill through the rock beneath it. The drill string would have to be several kilometers long before it even touched rock. The ship carrying the drilling equipment would be sitting on the surface, subject to waves, wind, and currents, while trying to maintain a fixed position over a hole in the seafloor with an accuracy of a few meters. And the rock itself, oceanic basalt, which forms the seafloor, has a hardness that makes continental granite look almost accommodating. Project Mohole was the American answer to this challenge. Conceived in 1957 by a group of geophysicists who called themselves the American Miscellaneous Society, the name was intentionally satirical. It was funded by the National Science Foundation and represented the most ambitious earth science project ever attempted at the time of its inception. The concept was to drill from a ship in the Pacific Ocean in water deep enough to ensure that the underlying crust was oceanic rather than continental, and to core through to the mantle. The first phase of drilling, conducted in 1961 off the coast of Mexico near Guadalupe Island, was technically successful. The project drilled through 183 meters of ocean floor sediment and into the underlying basalt, the first time the seafloor had been drilled to actual basement rock. The scientific results were significant, but the project ran into exactly the kind of problem that had not been fully anticipated. Drilling from a ship in deep water required solving a positioning problem that existing technology could barely handle. The ship, the Chikyu one, converted from an oil industry barge, had to maintain its position using a combination of anchors and propellers guided by acoustic transponders placed on the seafloor. In moderate seas, this worked, approximately. In rough conditions, the ship could not hold position well enough for drilling to continue. The second phase of Mohole, intended to actually reach the mantle, was designed to use a purpose-built drilling vessel with a more sophisticated dynamic positioning system. It ran into bureaucratic and political difficulties. Congressional critics questioned the cost, the management was disputed between different institutions, and in 1966, Congress canceled the project before the deep drilling phase had begun. The United States never drilled to the mantle, but other nations and international consortia continued. The Deep Sea Drilling Project, which succeeded Mohole, and its successor programs, the Ocean Drilling Program and the International Ocean Discovery Program, have drilled thousands of holes in the ocean floor over the past half-century, recovering core samples that have transformed the understanding of ocean crust formation, plate tectonics, and deep-sea biology. None of them has reached the mantle. The most ambitious current attempt is the Japanese drilling vessel Chikyu, which represents the state-of-the-art in scientific ocean drilling. The Chikyu is a purpose-built drilling ship carrying a derrick 21 stories tall and capable of drilling in water up to 2,500 meters deep, with a drill string of up to 10,000 meters. Its dynamic positioning system uses a combination of GPS, acoustic transponders, and computer-controlled thrusters to maintain the ship's position over a seafloor drill site with an accuracy of a few meters, even in moderate to rough sea conditions. It is, by any measure, a remarkable piece of engineering. Yet the Chikyu has not reached the mantle either. The technical difficulties of ocean drilling have proven more stubborn than the optimistic projections of the 1960s suggested. Ocean basalt is extraordinarily hard. The junction zones between tectonic plates, where the crust is thinnest and the mantle closest, are also the zones of highest geothermal activity and highest fluid pressure, conditions under which the rock is most prone to the plastic deformation that causes boreholes to close and under which unexpected gas and fluid releases are most likely. Several of the deepest ocean boreholes have been terminated by exactly these events: a sudden pressure surge, a burst of superheated fluid, equipment damaged or lost to conditions that no pre-drill survey had predicted with sufficient accuracy. The thin, oceanic crust that looked like the easy path to the mantle has turned out to be, in some ways, more difficult to penetrate than the thick continental crust. Thickness was never the only obstacle. Chapter 6. The Holes We Dig. While scientists were attempting precision exploration of the deep crust and mantle, industry was creating its own category of extraordinary holes. Not narrow, precisely positioned scientific boreholes, but vast open excavations that represent some of the most dramatic alterations to the surface of the planet that human activity has produced. These are the open pit mines, and the deepest of them descend far enough to generate phenomena that have no equivalent in any other human construction. The Mir kimberlite pipe in the Mirny district of Yakutia, eastern Siberia, operated from 1957 to 2001 and produced more than 10 million carats of diamonds over its operational life. Its dimensions are staggering, even by the standards of large mines. The pit is 525 meters deep, deeper than many skyscrapers are tall, and 1,200 meters across at its widest point. The volume of material excavated to create it exceeds 350 million cubic meters. In terms of volume displaced, it is among the largest holes ever dug. The Mir mine is officially closed to all aircraft. The prohibition is not primarily a safety measure designed to prevent crashes, though crashes have occurred in the area. It is a consequence of physics. The pit is a gigantic bowl in the landscape, and the air inside it behaves very differently from the air above the surrounding surface. On warm days, the air at the bottom of the pit is significantly cooler than the air at the rim. The rock walls and floor absorb heat more slowly than the surrounding vegetation and soil, and the depth creates a sheltered environment where cold air accumulates. This creates a strong temperature inversion within the pit, with cool, dense air at the bottom and warmer, lighter air above the rim. When a helicopter or light aircraft flies over the rim of the pit, it passes from the relatively warm, supportive air above the surrounding terrain into the zone of downdraft created by the temperature differential. The cool, dense air inside the pit flows outward and downward relative to the warmer air above it, creating a persistent downdraft that can strip lift from a rotary wing aircraft in seconds. Pilots who have experienced this effect describe it as the aircraft suddenly losing altitude with no mechanical cause, a physical version of flying into a hole in the air. The effect is most pronounced in summer, when the temperature differential is largest, and during the afternoon hours when solar heating of the surrounding terrain is greatest. At the bottom of the Mir pit, trucks that are too large to fit in a standard 2-lane road, vehicles with wheels 3 meters in diameter, cabs 5 meters off the ground, carrying loads of 130 tons, crawl along the spiraling haulage road that descends in a series of switchback curves from the pit rim to the working level. From the rim, these machines look like insects. From inside one of them, the walls of the pit rise like cliffs on every side, and the sky above is a distant circle of light. The temperature at the bottom is 10 to 15 degrees cooler than at the surface. Fog forms in the lower levels of the pit during certain atmospheric conditions, reducing visibility to near zero. Drivers navigate by instrument and radio communication. The operational risks of working in a deep, open pit mine are qualitatively different from those of surface mining. The haul roads descend several hundred meters on grades of up to 10%. A fully loaded haul truck weighing several hundred tons on a 10% grade is controlled by multiple independent brake systems, but brake failures on deep pit haulage roads are not hypothetical events. They have occurred, and the consequences are severe. Emergency runaway lanes, berms of loose gravel designed to arrest an out-of-control truck by forcing it to climb against a slope while the wheels dig into the gravel, are a standard feature of deep pit design, as are protocols for managing brake temperature on extended downhill hauls. In 2013, the Bingham Canyon copper mine in Utah, one of the largest open-pit mines in the world, at approximately 1.2 kilometers deep and more than 4 kilometers wide, experienced a landslide of approximately 65 million tons of material. The mass of rock and soil that moved in that event was sufficient to register on seismographs as an earthquake of magnitude 2.5. The event was predicted by the mine's geotechnical monitoring systems, which had been detecting increasing rates of ground deformation in the affected area for several weeks before the slide occurred. All personnel were evacuated from the hazard zone before the failure. No lives were lost. The Bingham Canyon slide is instructive not for its drama, but for what it illustrates about the nature of the engineering challenge in deep open pit mining. A hole more than a kilometer deep and several kilometers across is not a stable geometric feature. It is a dynamic structure in which the rock walls are in a continuous state of stress redistribution, creeping almost imperceptibly under the combined influences of their own weight, groundwater pressure, blasting vibrations, and seasonal temperature changes. Geotechnical monitoring, the continuous measurement of slope movement, groundwater levels, and acoustic emissions from the rock, is not a precaution in deep pit mines. It is what keeps them operational. But for all the scale of what industry has excavated, the perspective provided by geology reduces it to something almost negligible. The deepest open pit mine in the world descends approximately 1.2 kilometers. The continental crust it sits in is 40 kilometers thick. The deepest scientific borehole ever drilled reaches 12 kilometers, 30% of the way through the crust, not counting the mantle below. The total volume of material humanity has ever extracted from the Earth's subsurface across all of its mining and drilling history represents a vanishingly small fraction of the crust's total volume. We have been scratching the surface in the most literal possible sense. Chapter 7. The Next Frontier. The deepest boreholes currently in existence are not Kola. The records, as of the time of writing, belong to the oil industry, specifically to extended reach drilling operations in Qatar and on Russia's Sakhalin Island, where wells have been drilled to measured depths exceeding 12,300 meters. The Odoptu OP-11 well on Sakhalin, drilled by ExxonMobil, held the world record for total drilled depth for several years. But these wells are not going down. They are going sideways. Extended reach drilling, the technique used to drill these record-length wells, involves descending nearly vertically to a certain depth and then gradually curving the borehole to near horizontal, following a target formation that may be located many kilometers laterally from the surface location. This approach is driven by economics and by access constraints. A single offshore platform or onshore well site can access a reservoir spread across many square kilometers of area if the borehole is extended and deviated appropriately. The engineering challenge is extraordinary. Imagine threading a flexible needle from one side of a city to reach a specific thin layer of sand on the other side at several kilometers depth with an accuracy of a few meters, while the needle is rotating and the rock it is passing through is trying to close around it. During the drilling of one of these ultra-long extended reach wells in the early 2000s, an incident occurred that the engineering team found deeply disorienting. At a certain depth during directional drilling, the drill bit stopped responding to steering commands. The downhole telemetry, the real-time data transmitted from instruments located just behind the bit, showed the bit rotating in the opposite direction from the surface drive. This is, under normal mechanical conditions, impossible. The drill string is a continuous mechanical transmission. If the top rotates clockwise, the bottom rotates clockwise. The bit cannot reverse rotation without the string reversing. The explanation, once found, was a perfect demonstration of the unexpected behavior that emerges in mechanical systems at extreme scales. The drill string, tens of kilometers of steel pipe under simultaneous axial load, bending stress and torsion, had accumulated enough elastic energy from the rotation to behave like a compressed spring. When the bit encountered a hard formation that momentarily arrested its rotation, the energy stored in the twisted string was released explosively in the reverse direction. The effect was analogous to releasing a stretched rubber band, except that the rubber band weighed several hundred tons and its snap was measured in megajoules. The entire structure came close to catastrophic failure. The event did not result in a loss of the well, but it established a fundamental limit on the behavior of steel at length scales that had not been encountered before, and forced a revision of design parameters for subsequent ultra-long wells. The economic and practical ceiling for conventional drilling technology is now reasonably well understood. At approximately 15 kilometers depth in hard rock, the weight of the drill string itself begins to approach the tensile limit of steel. The pipe would begin to fail under its own weight before it could drill further. Temperature limits are also a factor. Standard steel drill pipe begins to lose its mechanical properties significantly above 250 degrees Celsius, and the temperatures at 15-kilometer depths in active geological zones can approach or exceed this value. Getting past these limits requires materials that do not yet exist in commercial quantities. High-temperature alloys capable of retaining strength and fatigue resistance at 300 degrees or more, combined with cooling systems that can maintain equipment functionality in an environment that would melt standard electronics. The scientific community has not abandoned the goal of reaching the mantle. The International Ocean Discovery Program continues to plan for a Mohole penetration in oceanic crust. The technical challenges are being addressed incrementally, with each drilling expedition extending the depth record and improving understanding of the conditions that will be encountered. The target areas for potential mantle drilling have been narrowed to specific locations in the Pacific and Indian Oceans, where the oceanic crust is at its thinnest and the local geology is most favorable. Project M2M, Mohole to Mantle, represents the current roadmap for the first direct sample of Earth's mantle. The project envisions the use of new drill bits designed specifically for ultra-hard oceanic basalt, new high-temperature electronics for downhole measurement, and possibly new approaches to borehole stability management that draw on techniques developed in geothermal drilling. The scientific case for the project is overwhelming. A direct sample of mantle rock would resolve fundamental questions about the composition and dynamics of the planet's interior that seismic data alone cannot answer. The engineering case is a question of will and resources. What happens if we succeed, if we drill through the oceanic crust and recover samples from the mantle, is a question that exercises some scientists who study geological hazard. The mantle is under enormous pressure. Drilling into it releases that pressure locally and introduces a channel through which mantle material, at temperatures above 1,000 degrees Celsius, could potentially rise. The risk is considered by most specialists to be manageable. The borehole would be tiny relative to the volumes involved, and the drilling would take place far from any populated area. But the uncertainty is real. We have never done this before. The planet's response to a penetration of its mantle layer is genuinely unknown. 12 kilometers down. That is the sum of everything humanity has physically achieved in its attempt to understand what it is standing on. The mantle begins at 40 kilometers in continental crust, at 5 to 7 in oceanic. We have probes beyond the solar system. We have mapped the surface of Mars in a higher resolution than many parts of Earth. We have detected gravitational waves from collisions of black holes billions of light years away. And we cannot reach into our own planet more than 12 kilometers without the planet pushing back hard enough to stop us. The most alien environment in the accessible universe may not be the outer solar system. It may be directly below us. A place of crushing pressure, extreme heat, chemically active water, ancient life, and sounds that human instruments can record, but human intuition cannot easily interpret. A place we have barely touched, despite everything. A place that, every time we reach a little further into it, surprises us in ways our models did not predict, and our intuitions did not prepare us for. The planet is older than our ability to understand it, and it is in no hurry to be understood.